All right, let's work 4.70. Question reads, if 25.98 milliliters of 0.1180 molar KOH is required, I forgot to write that, but potassium hydroxide aqueous is required to titrate 52.5 milliliters of acetic acid, CH3COOH. What is the molarity of that acid, okay? So this is basically a solution stoichiometry problem that revolves around a hypothetical titration. In such a titration experiment, maybe you've seen this before, maybe you haven't, okay? But typically what we might do is take a sample down here, okay? We're basically going to slowly add a titrant, which is a aqueous solution or material that is known to react with the component in our sample that we're trying to measure, okay? Now in this particular case, what I would do in this experiment in the lab is I would put my 52.5 milliliters of my acetic acid aqueous here in this flask. Now that's a volume. The acetic acid would have some concentration, some molarity inside that solution. Now, I don't know what that molarity is. That's what I'm trying to find in this problem. Okay? So I'll put question mark molarity because I don't know what that is, but by the end of the problem I will, right? Now what I'm going to do is in this long glass tube that's got tons of these graduations or volume marks on the side, this is called a burette. I'm going to fill this long glass tube up with a titrant. The titrant goes into the burette. Now in this case, the solution that I'm going to put in there is 0.1180 mole per liter potassium hydroxide aqueous. Okay, it's aqueous solution. And what I'm going to find experimentally when I drain that titrant into here, very carefully, is that 25.98 milliliters of that titrant is required to react exactly with my sample and to consume it perfectly, okay? Now, the way I'd figure out where the titration was over is I'd put an indicator compound into this flask. The indicator changes color when the titration is finished, when you've reached what's called the end point, okay? So that's how I'd visually detect. But I'd very carefully add my titrant until the indicator changes color, and that would indicate the end of the reaction or the consumption of my sample, the complete and total consumption of it through chemical reaction. In this case, that took a little under 26 milliliters. Based on this information, I'm to figure out what the molarity of my sample is, okay, the acetic acid in my sample. How am I going to do this? Well, we are running a chemical reaction in a titration. It's an acid-base titration. It might make a lot of sense to start with that reaction. Now, our sample, we already decided, contains CH3COOH. This is known as acetic acid. It's a primary ingredient in vinegar, acetic acid. It's a very simple organic acid. It often results from fermentation. This group right here, or arrangement of atoms, COOH, when you see that in a chemical structure, you should think a weak organic acid. It's called a carboxylic acid functional group. It should clue you off it's an acid. This proton, this H, is the acidic proton. This is the H plus that can come off and be titrated. These H's generally cannot be removed very easily. Much more easily removed over here. But nonetheless, I'm going to take that acetic acid. I'm going to react it with the strong base. Now here that's going to be provided by KOH aqueous. This is my titrant. I add that with my burette. Now what products am I going to make? Well, I'm going to take this hydroxide, pair it up with that H to make H2O, liquid. And in addition, I'm going to have some potassium acetate. Acetate has a -1 charge, potassium has a +1. This is going to be aqueous, okay? This is the resultant salt. So I made liquid and salt, again, just like we've been talking about, okay? This is my reaction. Now, is it balanced? It is balanced because acetic acids, called a monoprotic, MONO, monoprotic acid. It's got one proton that can be titrated, and only one. So it's a 1-to-1 ratio between the acid and the base. That's the chemistry that occurs. Now in this experiment, I was required to add 25.98 milliliters of this molarity KOH to reach the endpoint. That endpoint is when I've consumed all the acid that's in this flask, okay? So can I figure out how many moles of KOH was required? I think I can, because I remember molarity times volume in liters gives me moles, right? So what's my molarity? Well, of the KOH, it was 0.1180 moles per liter. And remember, my volume needs to be in liters for this to work well. So I'm going to convert by dividing by 1,000. So 0.02598 liters. And I do the math on that on my calculator. It looks like this titration consumed 0.003065 6 mole of KOH. So that's what it cost me to reach the end point, right? The number of moles of KOH to get there. Now, what does this have to do with the acid? Well, think about the reaction. Balanced chemical reaction. We said earlier it was a 1-to-1 ratio. For every one of these, we need one of these. For every one of these we use, we can consume one of these, right? So because of that, I can use the stoichiometry of my balanced chemical reaction to figure out how many moles of the acid must have also been consumed. So 0.00300656 moles of KOH were used. You might also say this is 3.06 millimoles. Sometimes you hear people use the prefix milli in front of moles. Millimoles. It's just using the metric prefix for mole-based units. Okay, nothing wrong with that. You can also call it 0.00306 if you want to keep things simple. But what the important thing is that in my balanced chemical equation, I know for every 1 mole of KOH, I can consume 1 mole of my acetic acid. And that's important because then I know that in this titration, I've also consumed 0.0030656 mole of my acetic acid. I've consumed equimolar quantities here, right? Okay, so it's the same number of moles. I think I cut off what it would adjust. So I've consumed the same exact number of moles. It's a 1-to-1 stoichiometry. Now, why is that important? Well, where did those moles come from? Or where were they when we started this reaction? Weren't they in this sample? So inside this flask, now I know that when I started this reaction, where I started this experiment, I had 0.0030656 mole of my acetic acid present. That's how many moles were present there. It had to be the case, because that's how many I consumed in the reaction. And I also know that the volume of that sample was 52.5 milliliters. So it's pretty straightforward then to compute my molarity, because molarity is just number of moles of my analyte or my material divided by liters of solution, right? This is a pretty straightforward calculation at this point, because my number of moles was 0.0030656 mole. And I'm going to divide that by liters of solution, which was 0.0525 liters, or 52.5 milliliters. I do the math on that. I quickly learned that the molarity of my acid in the original sample was 0.0584 mole per liter. So this is another example of a solution stoichiometry problem where you have to use mathematical equations like this and the definition of molarity. Okay. But we also got introduced to titrations a little bit here. Okay. You want to know what a titration is and what it's all about. It's usually to measure the concentration or the amount of a sample present in a flask. Okay. So this is another example.